Welcome to my channel Pharma Companion. Today we'll discuss about the topic infrared spectroscopy. So infrared spectroscopy deals with the infrared region of the electromagnetic spectrum. The infrared region or the infrared light have longer wavelength and lower frequency than the visible light. The IR spectroscopy generally refers to the interaction of the molecule with the IR radiation. The IR spectroscopy concept can be analyzed in three ways: by measuring reflectance, by measuring the emission, and the absorption of the molecule. Now, the range of IR spectrum lies between the visible and the microwave region. From 800 to nanometer to 1 millimeter is its range. So, as you can see in the diagram or in this image, uh, the infrared region lies from 800 to 1 millimeter, and after 1 millimeter there is microwave ranging starts, and before 800 nanometer the visible radiation starts. Mostly used IR region is near IR, which is 2.5 to 2.25 micrometer. Ranges of the IR: the first one is overtone or very near IR, which is 1.2 to 2.5 micrometer, and second one is vibration or near IR, which is 2.5 to 25 micrometer, and third one is rotation or far IR, which lies from 25 micrometer to to above than 300 micrometer. Now, the major use of IR spectroscopy is to determine the functional groups of molecule relevant to both organic and inorganic chemistry. IR spectrum is a graph that is plotted with the infrared light absorbed on the y-axis against frequency or wavelength on the x-axis. Means when the IR spectrum graph is prepared, the absorbance a molecule shows is shown on the y-axis, and the wavelength or frequency to which the molecule absorbs is shown on the x-axis. The IR spectroscopy detects frequency of infrared light that are absorbed by a molecule. Molecules tend to absorb this specific frequency of light since they correspond to the frequency of vibration of bonds in the molecule. So as you can see in this image, the IR spectrometer consists of first of all a radiation source from which the radiation passes to reference and sample, and their absorption occurs, and the transmitted wavelength or transmitted amount of light is passed to the chopper. Chopper collects the light and it then passes the light to the monochromator. Monochromator basically does the function of uh, separation of a monochromatic light from a polychromatic light, and then this monochromatic light is passed to the IR detector where the amount of transmittance and the amount of absorbance is detected. Now, let us discuss the principle of IR spectroscopy. The IR spectroscopy theory utilizes that a molecule tend to absorb specific frequency of light that are characteristics of the corresponding structure of a molecule. So, when a specific wavelength of light of infrared light is passed through a sample, the molecules of this sample undergoes vibrational changes by absorbing some of the light and by transmitting other light, which is called as transmitted light, and then this transmitted light is absorbed and the total amount of absorbance and transmittance are calculated in the IR spectroscopy. The energies are reliant on the shape of molecular surface, associated vibronic coupling, and mass corresponding to the atoms. After absorption of IR radiation, the molecules of a chemical substance vibrate at many rates of vibration and give rise to closely packed absorption bands called as IR spectrum. The energy required to excite the bonds belonging to a molecule and to make them vibrate with more amplitude, which occurs in the IR region. A bond will not react with the IR radiation unless it is polar. So, for a molecule to vibrate and react with the infrared radiation, it is necessary to, to have the molecule to be a polar compound. The presence of separate partial and separate partial positive and negative charge in a molecule allows the electric field component of the IR radiation to react and to excite the vibrational energy of a molecule. The change in the vibrational energy leads to the change in dipole moment of a molecule. The intensity of absorption depends on the polarity of the bond, Like symmetrical nonpolar bonds like N2 and O2 do not absorb any IR radiation as they cannot interfere with the electric field. So, what is the requirement for a molecule to absorb IR radiation? That means that how will we know that this specific molecule or sample absorbs IR radiation? It must have two qualities or properties. First of all, the correct wavelength of radiation. After absorbing the IR radiation of the molecule undergoes vibration at increased amplitude. Some of the radiation is transmitted and some gets absorbed. And for it to get absorbed, the wavelength of light must be specific to that molecular compound. Now the second quality it must have is electrical dipole moment. So molecules absorb IR radiation when they have dipole moment in them. That means partial positive and partial negative charge in them. Such molecules react with the IR radiation and absorbs the energy and undergo vibrational changes. Like molecules HCl, KCl, and acetic acid, they have a partial positive and negative charge in them. That's why they interact with the IR radiation and absorb it. And the molecules like N2 and O2 don't absorb IR radiation as they don't have any dipole moment in them. Now, as you can see in this example of ethylene, this first of all, ethylene doesn't have any type of negative charge in it. That's why there is no change in dipole. And when a bromine atom is replaced with the hydrogen atom, then the bromoethylene compound shows a change in dipole moment. Now, let's discuss the mode of vibration in polyatomic molecules. When a molecule absorbs IR radiation, it gives two types of vibrational changes. First one is stretching vibration and second one is bending vibration. Stretching, as you can see in this image, stretching occurs when two molecules go away from each other or come closer to each other and the bond angle doesn't change but the bond length change. And the bending vibration occurs when there is change in the bond angle and there is no change in the bond length. Now bending vibrations are of four types. First one is rocking, when two molecules go in the same direction and the bond angle changes, is called as rocking. Scissoring occurs. Second type of bending vibration is scissoring, and scissoring occurs when both the atoms come closer to each other and the bond angle between them is decreased. Third type of bending vibration is wagging. Wagging means when both the atoms move away or move closer to each other simultaneously and the bond angle increases or decreases. Now, out of the plane twisting is the fourth type of bending vibration, which occurs when one atom doesn't show any type of change. As you can see, there is a negative on one atom, which means that it doesn't show any movement, and there is a positive in one atom, which means that it shows particularly a movement, which increases or decreases the bond angle. Now, Fourier transform infrared spectroscopy (FTIR). As the normal type of dispersive infrared spectrometer has many limitations because it examines component frequency individually, resulting in slow speed and low sensitivity. FTIR spectrometer is preferred over dispersive spectrometer since it is capable of handling all the frequencies simultaneously with high output, reducing the time required for the analysis. The radiation sources used in the dispersive infrared spectrometer can be used in the FTIR spectrometer. But in contrast with the monochromator and dispersive spectrometer, FTIR spectrometer employs an interferometer. This is the main term used in FTIR, interferometer, instead of monochromator. The beam splitter within the interferometer splits the incoming infrared radiation into two beams, one of which it is reflected by a fixed mirror, while the other one is reflected by a moving mirror perpendicular to the fixed one. The length of path one beam travels is fixed, and that of the other one is changing as the mirror moves, generally an optical path difference between the two beams. So this is the common diagram of FTIR spectrophotometer, in which fixed mirror is used and moving mirror is used. As you can see from the bottom, infrared source emits the IR radiation towards the moving mirror. So from the moving mirror, it goes on to the fixed mirror on the above, and the fixed mirror reflects this IR radiation towards the moving mirror. The moving mirror again transfers this light into the beam splitter through the detector. And after the beam splitter, there is a missing sample is placed after the beam splitter before the detector. So by using this type of interferometer, by using the fixed mirror and the moving mirror, the amount of light that is absorbed by the molecules can be gradually increased by giving it more wavelength of light as as it normally absorbs from the IR source. So after meeting back at the beam splitter, the two beams recombine, interfere with each other, and yield an interferogram. The interferogram produces interference signal as a function of optical path difference. It is converted to a spectrum of absorbance or transmittance versus wave number or frequency by Fourier transform. Detectors used in the FTIR spectrometers are mainly pyroelectric detectors, means thermal detectors, and photoconductive detectors, means detection of the light. The former are constructed of crystalline materials such as deuterated triglycerin sulfate, whose electric polarization relies on temperature. The change in the temperature leads to the change in charge distribution of the detector, and electric signal is produced. The latter, such as mercury cadmium telluride, provides better sensitivity and faster speed than the pyroelectric detectors over a broad spectral range. However, liquid nitrogen is needed for cooling of photoconductive detectors because photoconductive detectors in the photoconductive detectors the cathode used can degrade due to high temperature. That's why liquid nitrogen is used for cooling. Now let's discuss about the chart of the infrared spectrum. So as you can see, this chart belongs to ethylene vinyl acetate. This is a transmittance chart. On the x-axis you can see the percent transmittance, percent T you can see, which is the transmittance of the compound, and this is the inverse graph. In the absorbance graph, you can see a normal type of graph with peaks, but in the transmittance graph you will see the inverse graph. So on the y-axis there is transmittance, percent transmittance. On the x-axis there is wave number, which is centimeter inverse. So in ethyl vinyl acetate there are um, how many stretches? One, two, three, and four type of stretches occurring in the ethyl vinyl acetate. The first stretch is the CH2 stretch, which occurs between around 3000 centimeter inverse, and the other CH2 stretch, which occurs beside it, around 2900 centimeter inverse, and the carbonyl stretch, C double bond O stretch, occurs around 1800 centimeter inverse, and there is a fingerprint region which lies from 600 to 600 to 1500 centimeter inverse. This is the absorbance graph. As I said you earlier, absorbance graph there is a normal type of peak or spectrum, and this absorbance graph refers to other compounds. Many type of compounds like H2O shows this type of graphs with nearly zero point 0.2 absorbance, and it lies between 3500 to 4000 centimeter inverse. And as for methanol, the graph is very low as it is not polar, as it is less polar than the water, and that's why its graphs come around 3000 centimeter inverse. Now as for CO2, it contains dipole moment, that's why its peak is the highest peak, and with zero point 0.8 absorbance and frequency around 25 2300 centimeter inverse. Now again for water there is given the peak, and for methanol also there is given this peak, and for carbon dioxide also the peak is given. Sampling of the substances. Now you can say that how will we put a sample in the IR spectrophotometer, if it is solid or liquid or gas. For your information, three three states of matter: solids, liquids, and gas. All the three states of matter, their detection is done by IR spectrometer. So first of all, the sampling of solids is done by first method, solids in solution, by dissolving the sample. First of all, the solid sample is uh, grinded thoroughly, and it is dissolved in the non-reacting solvent, and it is made then two parts. In first part, one drop one drop of the solid sample is put on the alkali metal, and the other half solution is placed in the sample cell made up of KCl or KBr or NaCl, which is alkali metal, and then the sample is studied or observed. Second type of the sampling of solids is solid films. This is done for amorphous solids, in which sample is placed over NaCl or KBr films or plates, and the sample is let to evaporate or dry, and then it is observed. This type of solid films technique is used only for qualitative study. Third type of technique for sampling of solids is mulling technique, which is the most popular, in which nozzle oil or mineral oil is used. In this, the procedure starts from grinding of the solid sample, then mixing it with nozzle, which is mineral oil, and this forms a thick paste. And this thick paste is spread between the IR transmitting window, and the observation is done. Now, the characteristic of nozzle or mineral oil is that it is transparent in the IR region, but its absorption maximized between 2915 to 719 centimeter inverse. And also, sometimes hexachlorobutadiene is also used with nozzle to improve its action. And mulling technique is also used for qualitative analysis. It is not used for quantitative analysis, but it is a very popular technique used in the exams mostly. Fourth type of technique is pressed pellet technique, in which the solid sample is mixed with the KBr powder, which is 100 times the weight of solid sample, and both are finally grinded first of all. Then a high pressure punch is used to form a pellet or a disc. This disc this disc is then studied or observed. As you can see in this diagram, KBr plus sample is pressed between a pellet and a small disc type of, like a tablet punching machine. A tablet or disc is formed, pellet is formed, and this pellet is then used for sampling. Now, what are the advantages of pressed pellet technique? It can be stored for a long time. Elimination problem of bands in the mulling agent can be eliminated, and its resolution is much superior than the mulling technique. Disadvantages of the pressed pellet technique: the band 3450 centimeter inwards is always present from the OH group. Okay. Now pressing may change the polymorphic crystallinity of the sample, and also it is not used for polymers because it is difficult to grind with the KBr sample. Now the sampling of liquids. For the sampling of liquids, they are put into the rectangular cells that are made up of alkali metal salts like sodium chloride, potassium bromide, or thorium bromide, which are made from 0.01 to 0.05 millimeter thickness, and liquid sample must be dried before cooling, as it can dissolve the NaCl cells, and it is used for quantitative analysis, but it is less precise in IR than UV. Now, how do we do the sampling of gases? For the sampling of gases, long cells are made from 10 centimeter long, and they may be 1 meter long, and these cells are made up of potassium bromide and sodium chloride cells, and multiple reflection can be used to make effective path length as long as 40 meters, so that all the constituents of gas can be determined, but it lacks sensitivity. As you can see in the diagram, from the left there is inlet of the gas, I'm sorry, it is not the inlet of the gas, it is inlet of the IR radiation. The gas is present inside the cell. We fill the gas inside the cell, the sample gas, and the in, there is inlet of the radiation from the left side, from one side of the cell, and the radiation counter interacts with all the constituents of the gas, and an effective path length of as long as 40 meter is made by uh, by multiple reflections inside the chamber, inside the cell, and after that the gas no the gas not the IR radiation is emitted and the transmitted wavelength is measured. Now, what are the applications of infrared spectrophotometer or spectroscopy? It is used for qualitative identification purposes, for finding the functional groups, their characteristic fundamental vibration, which give rise to absorption at certain frequency range in the spectrum. It is used for identification of functional group and structural elucidation. Entire IR region is divided into group frequency region called as the fingerprint region. Fingerprints means that as all the humans and all animals have different fingerprints for their identification, just like that, every molecule shows other type of spectral graph in the IR spectroscopy. That's why they are called as fingerprint region, because they have their own identity, they have their own type of IR spectrum. That's why the fingerprint word is used in this. So IR spectroscopy is used to establish whether a sample of organic substances is identical with another or not. It is used in the group frequency region. The peaks corresponding to different functional groups can be observed. According to the corresponding peaks, functional group can be determined. Each atom of the molecule is connected by a bond, and each bond requires different IR region, so characteristic peaks are observed. The region of this IR spectrum is called as fingerprint region of the molecule. It can be determined by characteristic peaks, and also it is used for quantitative analysis. Absorbance is used for quantitative analysis due to its linear dependence on concentration, and the formula A is equal to epsilon Cl, where C is concentration, L is the path length, A is the absorbance. Now, it is also used for studying the process of reaction. Progress of a chemical reaction can be determined by examining the small portion of reaction mixture withdrawn from time to time, and this uh, variance in the sample is then measured. The rate of disappearance of the characteristic absorbance bond of reactant group, or rate of disappearance of characteristic absorption band of product, can determine which of the new product is missing or which of the new product is formed in it. Now, IR spectroscopy is also used for detection of the impurities. IR spectrum of the test sample to be determined is compared with the standard compound. If any addition peaks are observed in the IR spectrum, then it is due to the impurities of the compound. Now, these are the references from which I referred for making these slides. Thank you so much for watching. Please do subscribe and like all my videos. Thank you so much.